Good afternoon. As president of the University of Chicago, I have the honor of welcoming you to this very special event. Just a few hours ago in Stockholm, the King of Sweden awarded this year's Nobel Prizes, including one to Yoichiro Nambu, Harry Pratt Judson Distinguished Service Professor Emeritus in the Department of Physics and the Enrico Fermi Institute. We thank Professor Nambu and his son John, who is here today, for allowing us to share with them this moment of remarkable achievement and celebration. It is my privilege also to introduce the Swedish ambassador to the United States, Jonas Hafström, who has traveled to Chicago on behalf of the Nobel Foundation and the King of Sweden to present the medal and diploma to Professor Nambu. We are also joined by university leaders and trustees, including the chairman of the Board of Trustees, James Crown, and by friends and colleagues of Professor Nambu, including members of the University of Chicago Physics Department. I would also like to acknowledge that here with us today are other Nobel laureates from the University of Chicago and from other institutions in the United States. In a few moments, we will watch a portion of the Nobel ceremony that took place in Stockholm earlier, including the presentation of the prize in physics. But first, I would like to say a few words about Professor Nambu's achievement. As you know, the University of Chicago has had the good fortune to have many of its leading scholars recognized by the Nobel Prize since the inception of the prize in 1901. In 1907, Albert Michelson, a faculty member of the University of Chicago, became the first American scientist to win the Nobel Prize. Professor Nambu's work exemplifies a defining element of the culture of the University of Chicago and a key part of its ability to advance knowledge and improve lives. And that is a rigorous inquiry, often across disciplines, that is inspired by a deep commitment to intellectual discovery. This intensity has been part of Professor Nambu's career here at the university for over 50 years. His investigations in subatomic particle physics have helped redefine the field and continue to be explored by researchers and laboratories throughout the world. He is still asking the questions that animate further discovery. As he has said, he thinks about them all the time. Professor Nambu's work in symmetry breaking in subatomic particle physics have become, in the words of fellow laureate Jim Cronin, the cornerstone of the standard model of particle physics, which unites the strong interactions, the electromagnetic interactions, and the weak interactions, all in a clear and understandable whole. Professor Nambu's achievements over the last half-century, culminating today in the awarding of the Nobel Prize, are a compelling reminder of why we work so hard to sustain the university's distinctive culture. We are grateful for his contributions to the university in particular and to human understanding more generally. May I ask that you now turn your attention to the screen to view a portion of the ceremony in Stockholm. Following this viewing, I will be joined on stage by Professor Nambu, Ambassador Hafström, and Chairman Crown. I am pleased to introduce Jonas Hafström, Ambassador of Sweden to the United States of America, who will present the Nobel Medal and diploma to Professor Nambu. Ambassador Hafström has served as a representative to our nation for over a year, part of a long and distinguished career in public service. Prior to this position, he served as Ambassador of Sweden to Thailand. Ambassador Hafström is also a non-commissioned reserve captain of the Swedish Army. For his outstanding work on behalf of his country, he was recently awarded the Seraphim Medal by His Majesty the King. Ambassador Hafström.
Thank you. Professor Nambu, President of the University of Chicago, Robert Zimmer, distinguished participants and guests, ladies and gentlemen. As the Swedish ambassador to the United States, I am honored to attend today's Nobel ceremony at the University of Chicago to present the Nobel Prize in Physics to Professor Nambu. It is a privilege for me to convey to you, Professor Nambu, the warmest congratulations of the Royal Swedish Academy of Science. On behalf of His Majesty the King, Carl XVI Gustav, I will now present the 2008 Nobel Prize in Physics. I now ask you to step forward to receive your Nobel Prize.
Thank you. Thank you, thank you, thank you, thank you very much. Thank you. Mr. Ambassador, Mr. President, and distinguished guests, and ladies and gentlemen, I regret I am not be able to travel to Stockholm, but I'm most honored and thankful to have this ceremony being held for me today. 2 days ago, my old collaborator, Gianni Jonas Senior of Rome, gave a Nobel lecture in Stockholm on my behalf. And I've just seen now on the screen, Professor Hafström gave an excellent summary of the significance of my work. And also the letter of invitation you have sketched out briefly my background. So I'll give here a short narrative of how I was led to the work for which I got the prize. My account will be a little slightly different way to present the meaning of my work. Physics is a single unified discipline, but there are various subfields. One of them concerns the basic constituents of matter and the laws governing them. Particle physics, so-called particle physics, is at this most fundamental level. Another area concerns the properties of aggregates of matter, particles, which are more familiar to us in my daily experience. So condensed matter physics, so-called condensed matter physics, is one of such fields. In the latter case, condensed matter, there are special laws that apply to them when large numbers of such elements get together. Spontaneous symmetry breaking, what is called spontaneous symmetry breaking, is one of them. Shortly, it's shortened, we call it SSB instead of a long name, spontaneous symmetry breaking. SSB arises due to a kind of group mentality, group psychology among the constituents. I came up with this metaphor when I gave a speech in the morning of October 7th before press. So I repeat it here for you today. Suppose a large number of people gather together in a large open area. This is one of such occasions. And there is no particular direction to which one could look interesting in general. So each one may be looking around into any direction. Any direction is equivalent. But there are some instances, all people will face one direction, like you are doing now. Well, suppose some curious one thought he saw something in one direction. Then the people around him will follow suit and look in the same direction, and so on and so forth. So soon people are looking toward one direction at all. That's a broken symmetry, what you call. Now, how do you know that, suppose this room was the whole universe, and everybody looking toward here. How do you know that the law of physics is equivalent in any direction? How do you know that? Well, maybe some curious one of them, are free to look around a little bit, because you know the distance to it, because all directions are equivalent. Then people around him will follow suit and start looking at this one. Then this will propagate like a wave from the sky out. That is called Nambu-Goldstone wave or Nambu-Goldstone particle in the case of particle physics that characterize the broken symmetry. So going back to my career, I studied physics at the University of Chicago, especially Tokyo, in the early 40s. I was attracted to particle physics, which was a brand new field at that time, by the famous two Japanese physicists, Hideki Yukawa and Shinichiro Tomonaga. Both would become Nobelists sooner or later. Yukawa started out maybe particle physics by predicting there should be a new particle that's the agent of binding protons and neutrons into various nuclei. Tomonaga, on the other hand, laid a cornerstone of the theoretical formalism that described particle physics. But these professors are not at my university. I was lucky to be able to get into their circle through a kind of GBS means by learning from students, more advanced students who were working with them. Somehow made myself into their circle. But in hindsight, I think I was fortunate that this university, Tokyo, was very good at condensed matter physics, and I learned it quite well. And in hindsight, my knowledge both of particle physics and condensed matter physics turned out to be very beneficial to me later. I came to the States in 1952 on the recommendation of Professor Tomonaga, and eventually settled at the University of Chicago here for over 50 years. And I was again fortunate, I must say, that this was a great place with great names like Enrico Fermi, Gregor Wenzel, Maria Goeppert-Mayer, Harold Urey, a chemist, gave me an excellent milieu in which to work with interdisciplinary. I was able to carry out interdisciplinary studies on this course. My ideas about this SSB arose in an effort to understand the so-called BCS theory of superconductivity, which happened at our neighbor institution, University of Illinois, not far from here. And although I was very impressed by that theory, success of that theory, I was struck immediately by a lack of symmetry that should be there if you follow the fundamental laws of physics. And I tried to resolve that conflict. I struggled for 2 years, and finally I reached the conclusion that that was SSB that I'm talking about today. And then realized that this phenomenon is not new at all. It has been known for many, many years, for a century or so, in day-to-day physics, in the name of, for example, in the matter of property of crystals or magnets, and so on and so forth. But it was not recognized as a general organizing principle. Once I got this idea, I immediately tried to apply this back to particle physics. One of the mysteries of particle physics is that various elementary particles, so-called elementary particles, have different masses. According to particle physics theory, the mass symmetry, mass is not a symmetry and actinium. That the mass of symmetry breaks what we call chirality. It's an esoteric word, but handedness, actually, it's very difficult to explain what it means. And if the chirality was to be the law of nature, then all particles should be massless, no mass at all. So I suggested that the symmetry was broken spontaneously in that case, in nature. How do you know that? Because there is a Nambu wave associated with it. That is known also in particle physics. And that particle is nothing but what the Professor Yukawa had predicted to exist. Nowadays, the principle of SSB is a key concept in understanding why the world is so complex as they are, in spite of the many symmetry properties in the basic laws that are supposed to govern it. The basic laws are very simple, yet this world is not boring. That is, I think, is an ideal combination. Thank you. Thank you. Yeah. Thank you.
Professor Nambu, your work has greatly enriched the world's understanding of particle physics and has contributed importantly to the University of Chicago's unique culture of rigorous inquiry. On behalf of the faculty, students, staff, alumni, and trustees of the University of Chicago, I thank you and congratulate you. Excuse me. Let me also thank Ambassador Hafström and all of you in the audience and watching online for being a part of today's event. Following the brass fanfare that will close the ceremony, I invite you to make your way to the lounge down the hallway for a reception, which will begin with a champagne toast led by University Provost Tom Rosenbaum. Thank you.